Hello, my name is Hamid Haydari and I will talk about the background and existing challenges to the city of Henderson and its water reclamation facility. University of Nevada, Las Vegas student chapter of Nevada Water and Environment Association suggests upgrading City of Henderson Kurt R. Segler Water Reclamation Facility for biological nitrogen removal. Ikala Khan, the professor in Civil and Environmental Engineering and Construction Department at University of Nevada, Las Vegas, is the faculty advisor in this project. He assembled the student group and supervised the development of the design documentation. Feedback, regulations, and design considerations were provided by Sabrina Rivera, who is our project advisor from City of Henderson Water Reclamation Facility. She also provided input and helped coordinate with the City of Henderson Water Reclamation Facility administrators for background data. Hamid Haydari, Padmanabhan Krishna Swamy, Yasamane Saidi, Julian Guerrero are the presenters, and other members are Saeed Masroora, Qazi Shafat Haidar, Neil Christian Tugadi, Nina Ejada, and Amanda Page. Henderson is the second populous city in Nevada that is adjacent to Las Vegas. The population of city of Henderson is almost 330,000, and their main wastewater treatment plant is Kurt R. Segler Water Reclamation Facility. This facility was constructed in 1994 and upgraded in 2008. The treatment capacity of Kurt R. Segler is 24 million gallons of wastewater per day. The influent to the facility divides into two sides, west side and east side. The west side can treat wastewater up to 18 million gallons per day, and remaining 6 million gallons per day goes to the east side. This facility mostly treats domestic wastewater. You can see effluent amounts of selected parameters at the end of the table. The influent data that our student chapter was authorized to use was between 2012 and 2016. The facility flow profile in 2015 was chosen because the maximum and minimum effluent throughout the year is quite visible. As it is demonstrated in the graph, around New Year, the influence to the facility increases, which is due to the fact that Las Vegas is an international tourism destination, and for financial savings, some of the tourists reside in city of Henderson. The facility does not have primary clarifier, as they want to exploit all the organic capacity they can get to remove nutrients. The design of the plant centers around the activated sludge treatment, which provides biological treatment. The raw sewage enters the bar screening to wash and the water debris before discharging it into garbage can. This rainwater flows to an aerated grid chamber that facilitates the sedimentation of heavier inorganic materials. Then, two horseshoe-shaped basin oxidation ditches that each can treat up to 12 million gallon wastewater per day treats wastewater. Treated wastewater then pumps to secondary clarifier and then separates into wastes and treated water. The waste activated sludge goes to solid waste processor, and some of it goes back to the oxidation, which is to increase the sludge for biological removal. Treated water goes through a series of filters and disinfects by UV and discharges to the environmental buffer, here Lake Mead. A hydraulic model was developed to simulate the hydraulics of the treatment plant based on existing plans. Common system to use in a wastewater treatment plant is using gravity flow to save energy and costs. But City of Henderson Water Reclamation Facility uses pump system to generate flow with enough power to overcome pressure induced by the load at the pump outlet. The main concern identified by University of Nevada, Las Vegas, Nevada Water Environment Association student chapter is the nitrogen removal. Although there are other concerns such as damaged structures, rusty equipment, debris that pass behind grid chamber, and stagnant zones behind blowers in oxidation ditches that exacerbates the main concern, causing decrease in the efficiency of nitrogen removal from wastewater in current oxidation ditches. We evaluated the facility conditions and considered economical crisis caused by COVID-19 and suggested a design that will work to 2015 so City of Henderson does not need any more upgrading before that time. According to our estimates and future demographic data released by City of Henderson Municipal, the population will increase to around 555,000 and facility requires to treat up to 32 million gallons wastewater per day. The considerations for upgrading revolves around total nitrogen removal for future regulations, but also it is applicable for other future concerns such as total phosphorus, trace organic compounds, and total dissolved solids. There are different regulations that City of Henderson Water Reclamation Facility has to comply, but discharge permit is of the great importance due to algal bloom that occurred at Lake Mead in 2001. Discharge permit monitors the effluent quality into Las Vegas Wash and Lake Mead to maintain and protect the beneficial uses of Lake Mead, such as propagation of aquatic animals and wildlife, supply of municipal and industrial water, and recreational activities. The goal of our group is to improve and enhance nitrogen removal by introducing a cost-effective and energy-saving process. Compliance with future regulations also was taken into account.
Hello, I am Padmanabhan Krishnaswamy, currently pursuing my Masters in Civil and Environmental Engineering at UNLV. I will be talking about the alternatives and the decision matrix that led us to choose the most suitable alternative. We took 6 alternatives into consideration, as you can see from the slide. They are the modified UCT biological nutrient removal process, the modified Johannesburg biological nutrient removal process, modifications to the current existing secondary treatment system, membrane bioreactor, modified Barfendo process, and the A2O process. In order to help us decide which alternatives to choose, we used the Kepner-Turgot method to develop a decision matrix. The key factors taken into consideration in the decision matrix are the 50-year present value cost, social and environmental elements, treatment considerations, regulatory compliance, and the ease in implementing the process. Each alternative, the key factor will have a score weight in the range of 1 to 10, and the alternative that receives the highest total score will be the one chosen for the design. In order to score each process, their respective advantages and disadvantages are compiled and taken into consideration. If you notice, this slide will not contain the modifications on the current secondary treatment system, because the biggest advantage it possesses is that it is the least expensive to implement. Based on the score weights for each criteria and subcriteria, the performance score for each alternatives were calculated. Details regarding the calculation are provided in the report. As you can see from the highlighted portion, alternative 3 which is the modification to the current secondary treatment system, received the most score. So we decided to go with that process in the upcoming steps. In the chosen process, the most economical approach for modifying the current system is to provide an anoxic zone prior to the existing ditch. On doing so, nitrification can be achieved in the anaerobic zone and denitrification can be achieved in the anoxic zone. However, mixers will be needed at the anoxic zone in order to keep the biomass from settling. So by choosing this process, the advantages include ease in implementation. It's very simple to operate. It also uses less energy than extended aeration. It has well-stabilized sludge with low biosolids production. And most of all, it's the most economical alternative.
Hello everyone, I am Yasaman, a PhD student at University of Nevada, Las Vegas. In this slide, I'm gonna go over proposed modified process design diagram. The existing biological treatment consists of influent coming from pumping station, goes to oxidation ditches, and then it goes to our sludge handling system. In the modified existing secondary treatment system that we are going to propose, we are adding anoxic zone prior to oxidation ditches to improve our nutrient removal. In our process design specification, the recommended dimensions for anoxic tanks are shown in this table. You can see the typical value for depth for a circular tank will be between 9 to 16 feet, and the range for diameter will be between 9.8 to 196.8 feet. And the bottom slope inch per inch would be 0.045 to 0.063. The reason that we chose a circular tank for our design is because we can reach high quality mixing in the circular tank, and a circular tank design is less vulnerable to corrosion compared to the rectangular. The anoxic tank design is for 18 million gallon volume as influent. With the consideration of space availability and ease of maintenance and operation, 3 million gallon per day capacity of the tank is chosen with a retention time of 3 hours. And then the depth was calculated to be 14.76 feet, which was in the range. And then the diameter was 65.74 feet, which was again in the range that we can design for our circular anoxic zone. The total number of tanks that we need for 18 million gallon per day wastewater was 6, and we need 1 spare tank. So in total, the number of tanks required for treating 18 million gallon per day wastewater is 7. This is a modified process design diagram for the secondary treatment system. Here we have influent coming from pumping station, and here the 6 anoxic zone tanks that we proposed with 1 spare tank. And then after this stage, the flow goes to 2 oxidation ditches with a capacity of 12 million gallon for each. And then we have secondary clarifier and sludge handling system. The advantage of modified process design is to have greater efficiency of nutrient removal, is to minimum construction space required, and then no training needed for the operators in the wastewater treatment plant.
Hello everyone, my name is Julian Guerrero, and I'll be talking about the specifications for the design and the cost analysis. Specifications for design. Here we have a table indicating each specification for our proposed design. Our design will be for a projected 30 years. It will include 7 anoxic tanks that have a capacity of 375,000 gallons per basin. Furthermore, it will include 7 radial flow impeller mixers, and 6 pumps that have a capacity of 120 horsepower. Cost analysis. Here we have the table that shows how we did our cost estimations. We analyzed data from past studies and the RSMeans database to come up with estimations that reflect 2020 prices. Looking at the column labeled unit price, the unit price for each category except for pumps shows assumed adjusted 2% inflation. The cost for the pumps was found separately through the RSMeans database. The cost estimations are as follows. 7 anoxic basins will be $3.6 million. 7 mixers will be about $3.7 million. 6 pumps will be about $150,000. Replacement mixers will be $7.3 million. This results in an estimated total capital cost of $14.8 million. Assuming a 10% contingency and 2% insurance, the total cost for a proposed project becomes $16.5 million. Summary and recommendation. To reiterate, we recommend anoxic ditches because they provide excellent treatment and are simple to operate. Secondly, we recommend to modify the current secondary treatment system to include anoxic zone to achieve denitrification to meet the more stringent discharge standards. Furthermore, to reduce corrosion in the basin, we recommend epoxy-based powder coating for the inside wall and the floor of the basin. The University of Nevada, Las Vegas design team would like to acknowledge the support and guidance from Sabrina Rivera from the city of Henderson. We would also like to thank Dr. Khan for his review of the design process. This concludes the end of our presentation. On behalf of the University of Nevada, Las Vegas, and WEA design team, we would like to thank you for watching our presentation.